Okay, 1.9 Part 3 starts with the variation problem. And so before we actually go through the problem, let's talk about variation. Variation is how two or more variables will vary from each other. So that you have three different types of variation. The first type of variation we can have is direct variation. And so if it's direct variation, that tells us that we're going to multiply. So we'll have like, I don't know, y equals k, which is our constant of proportionality, or constant of variation. Always, all of them will have an equals k, and then it would be times whatever's afterwards, the x. Another type of variation we have is inverse variation. And so with inverse variation, we will divide. So our problem would look something like y equals k divided by x. And then the last type of variation we can have is joint variation, which means we're going to multiply with more than one variable. And so that might look like y equals k times x times z, where there's more than one variable afterwards. And they can be joined together. It could be direct variation and then very inversely. And so you could have multiplication and division in the same problem. Alright, so looking at this problem here. Example 7. It says Hooke's law for spring states that the distance a spring is stretched or compressed varies directly as a force on the spring. A force at 275 newtons stretches a spring 0.2 of a meter. How far will a force at 620 newtons stretch the spring? Alright, so what they gave us at the very top up there is going to help us set up the problem, and it's going to help us solve for k, that constant proportionality, or the constant of variation. Alright, so, and it's always in order for us. It says that the distance a spring is stretched or compressed. So that's my first part, because then I see that word varies. Okay, so the distance varies means equals k. Directly, we see to the side there, the directly means we're going to multiply. Multiply by what? As the force on the spring. So let's do an F for force. The next sentence is going to give us our two variables so that we can solve for k. So it says a force of 275 newtons stretches a spring 0.2 of a meter. And so we're just going to solve for k. So divide by the 275. And we get k equals, so let's see, 0.02 divided by 275. Yeah, and look what we got. Oops, I typed mine in wrong. Just one second. We got 7.273 e to the negative 4. Remember that e is the same thing as times 10. And the negative says we're going to move to our decimal to the left, and the 4 tells us how many places. So 1, 2, 3, 4. Alright, so we found that k is equal to 0.007273. Alright, now if you wanted to try to make this into a fraction, it is possible, but you can't use your rounded value, okay? So you have to do the 0.0007272727272, quite a bit of them, because it just keeps going, and then hit math, enter, enter, and it does tell us that this is the same thing as 1 over 1375. Okay, so you can use either value you want, but now what we've got is we've come up with this equation. Our equation then is d equals, we know that k, I'm going to use the fraction, times the force. And so if I know any distance or any force, I can solve for the other variable. So A says, how far will a force of 620 newtons stretch a spring? Well, newtons is my force. So we got d equals 1 over 1375 times 620. So let's solve that. And I got 124 over 275. And I want to take that back to decimal so that makes sense to us. And so I got 0.451 of a meter. Now, if your calculator gave it to you as a fraction, if you go back to math and you look at number 2, it says decimal. So you choose it and then hit enter and it changes your answer back to a decimal. All right, B says, what force is required to stretch a spring 0.1 of a meter? Well, that's my distance. So if I have 0.1 is equal to my K times F. And so I'm going to multiply by the reciprocal, or I just say it's by the denominator. When I do this, I get, so 137.5 equals F. And so we know then that the force would be 137.5 newtons. Alright, and then example 8 is talking about writing regression equations. So it says the U.S. bottled water producers' revenue in billions of U.S. dollars from 2005 to 2012 is shown in the table at the right. Use a graphing utility to write a regression equation. The time in years is given by T. So number 1 says create a list or spreadsheet of the data with T equals 1 corresponding to 2005. So we're going to let 1 be 2005, which means 06 is 2, 07 is 3. And guys, just make sure that your numbers are numerical order. Like if they'd have skipped this one, if this one would have been 2009, then this would have been 5, not 4, okay? But it's not. It's 2008, so that's another year. So 5, next year, the next year, and the next year. They didn't try to trick us, but a lot of time I'll see they'll take one out, and y'all will miss it. All right, so we're going to create a list in our calculator. And so to create this list in our calculator, we're going to go to Stat, which is right below Delete, next to the X button. So we're going to go Stat, and then we're going to choose number 1, which is Edit. When we do this, it's going to give us this table. And it's got a bunch of L1, L2, L3, so forth. We're going to put our X's in the first one and our Y's are in the second one. So let's do that. Alright, so go ahead and pause if you need to because we're going to jump on ahead here. So pause and put those in your calculator. Okay, so once you have those in your calculator now, 2 tells us create a scatter plot of your data and determine the best type of regression model. So in order to do this, we're going to go to second, Y equals, and you'll see this as stat plot. We're going to go into Y1 and we're going to turn it on. Now the rest of it's usually set. We want the scatter plot, which is the first type. Our X's were in L1, our Y's were in L2. Some of it, what kind of mark do we want it to make? And then some of us have where to say what color do we want it to be in. Alright, so once you turn on your stat plot, in order to get your graph to graph without us having to play with that window, if you'll go to Zoom and go find where it says Zoom Stat. I believe it's number 9. Yes, number 9 says Zoom Stat. Forgot to put number 1 was the Y1. Alright, so Zoom Stat. And what that does is it takes the list that we put in our stat edit, it looks at those numbers, and it creates the window for us. Alright, so check it out. Does yours look like the graph that we have there on number 2? It should look very similar. If you have some points that are like way off or some points that are missing, that means you have a typo. And I strongly encourage you, when you type these in your calculator, guys, go back over and make sure you don't have a little typo. Because when I was doing it a minute ago, with that $10.60 there, I accidentally got the decimal and the 0 mixed up. So I had 1.060. So make sure you check it. Alright, so I'm going to move up my graph here so I can see what the paper looks like. So that is what my graph looks like. So it says below we see linear on the left and cubic on the right. So what they did is they matched up, they found the equations for them and graphed it to see what it would look like. So how can we find those equations and how can we make it graph on ours so that we can see it? Alright, well let me just move on up here. Okay, so what we can do is we're going to go back into our stat. But this time we're going to right arrow over to calc. Alright, from there, if you notice, starting with number 4, you have lin-reg, which is linear regression. Then you have quadratic regression, cubic regression, quartic regression, another linear regression, natural log regression. It just keeps going and going and going. So the first one we want to do is linear. So let's choose number 4. Now, we have different types of calculators. Some of y'all will just have lin-reg. I think it says AX plus B. Okay, and that's all you're going to have on your screen. Okay, the rest of y'all who have newer calculators, you'll see that lin-reg at the top with the AX plus B. You'll also see like X list, and it says L1. You'll have Y list, which is L2, which is default in both calculators. You'll see frequency list, which there's nothing there. Then you're going to see store regression equation, okay? And then it'll say calculate. If we want to make our calculator save that equation, we can go to where it says store regression equation, or just where you're at if you're on the other type of calculator, okay? So right afterwards, either way, we're going to go and we're going to hit either here or here. You're going to hit vars, which is right next to clear. I messed up. Let me go grab mine again. I went in the right place to do it. So vars. Then we're going to right arrow over to y vars. It's a function. And then it asks where do we want to put it. We'll just put ours in y1. And then we can either hit enter or calculate, whichever one you've got. And so you'll see y equals ax plus b, y equals, and it's got a number, and b equals, it's got a number. So those are our equations. So let's see. I'm going to write this out. I'm going to round each of those to 3 decimal places. This was for linear. So y equals 0.126 x plus 10.407. That's my linear equation. Now, if you go to y equals, in y1 you have that equation that it found, okay, not rounded. And if you go to graph, you'll see that linear line going through the graph, just like what we have in this first one, right above where I wrote this equation at. All right. Now, since I'm going to do the same thing with the next one, but we'll just put it in y1. It'll be this fine. All right, so now let's run cubic regression. So remember, go back to stat and calc right here. And this time we're going to choose cubic regression, which would be number 6. All right, if we wanted to store our equation, we're going to type in that vars, y vars, function, y1, and then hit enter or calculate. You should see y equals ax cubed plus bx squared plus cx plus d, and it tells us what a, b, c, and d all are. All right, so I'm going to write that down. So I've got y equals 0.049 x cubed minus 0.6660 x squared. I went ahead and put an extra number on there. Plus 2.693 x plus 7.906. If you look in your y equals, now in y1 we have that, and if we hit graph, it will graph it. So which one looks like it's a better fit for the data that we've given? Yes, so for the data that we've been given, it looks like this cubic's a better fit. But now remember, that's only for the data that's given. Any data that lies outside of this might not agree with that. Because think about a cubic. A cubic, as it leaves this graph, it's going to go down really quick and it's going to go up really quick. Where in here, it didn't go up or down quite so fast. So it could make a difference in some things. Alright, so 4 says to use your model to predict bottled water revenues for 2018. It says don't forget that T equals 1 represented 2005. So in 2018, T would equal 14. And so we could use our table that we have up above to help us if we need to. Or if we know that 1 was 2005, that's a 4-year difference. So 14 would be 2018, 4 years. Okay, so we're going to check it in linear. So in linear, we plug that in to be our x. So we got y equals 0.126 times 14 plus 10.407. Now remember, these are rounded values, so they're going to be off just a little bit. If you're using a longer equation, your answer is going to be more correct, but it might be different a little bit. And I got 12.171. Now let's try it for the cubic. Now the cubic equation, remember, is still in our y1. So because of that, if we wanted to, now granted, we could plug the 14 in for all 3 of these x values, okay, and solve it that way. Or we can go to our table and find where x equals 14, what is the y value. Or you go to second trace value, and you can find it that way by putting in 14, if your window is big enough. Alright, so I can see that at 14 it's 49.380. And if you wanted to find that third decimal place, if you'll move over on top of the 49.38, it'll show you it is a longer number, so you can round it correctly. Alright, so here is the revenues of the bottled water in 2018 per different functions here, different models. So which one's going to be more correct, do you think? Well, the data that we looked at looked cubic, and I agree that I think the cubic one would be more correct for that data, but remember, it goes up really quick. When you look back up at your table, make sure you got all this because I'm about to erase it. When you look back up at the table here, you notice that, whoops, let me get up to the table, the numbers are like 10.01, 10.86, 11.18, there's 10.69, 11.82. In 4 years, do you really think it's going to jump up to 49 point something, or do you think maybe it'll go up to 12 point something? Yeah, the 12.171 sounds more realistic. So I think for data outside of the numbers that they gave us, the linear would probably fit a little bit better than the cubic, but for the data that they gave us, it definitely looked more linear.